1, 2, 3, 4, 5, 9. All right, class. So we are skipping 13.3. This week is 13.4 and 13.5. Okay, so the definite integral, what we're talking about here is the area underneath the line when they say definite integral. So before we've looked at like this, we have a function or whatever, and let's see, what's our fundamental theorem of calculus? Let me write it like this. The integral of the derivative was the function, okay? So here is the derivative of the function, and this was the antiderivative, and you get your function back, all right? So the derivative gives you the slope. What's the opposite of the derivative? All right, the opposite of the derivative is the area underneath a function. Let's see, suppose a car travels along a straight road at a constant speed of 50 miles an hour. The speed of the car at the time t is given by this constant function v of t. So this is a simple case where you're traveling at the exact same speed. You're not accelerating or decelerating, all right? So here is a graph, time, velocity, and if you're always at 50, it's just a constant, okay? How far does the car travel from time 2 to time 6? Well, here's 2 and here's 6 as far as time goes, but this is, excuse me, velocity, right? Since this is a 4-hour period, the answer, of course, is 4 hours times 50 miles per hour is 200 miles. Notice that 200 is exactly the area underneath the curve, okay? And the speed of the function v, underneath the curve. So when I say underneath the curve, I mean between the axis here, the t-axis, and the function, okay? So we saw in chapter 12, the speed of the function is the rate of change of distance. So velocity is the rate of change of distance, right? With respect to time. That is the rate of change of the distance function s, they use s instead of x. Is whatever, if you're traveling along a curve, they call it s. Okay. There we go. Now the distance traveled from time 2 to time 6 is the amount that distance has changed from 2 to 6. In other words, the total change in distance from, so this is v, but yeah, the change in position with respect to time is the velocity. I need a better picture than this. Yeah, you're looking at the total change in distance. This is the change in distance. That's your velocity, right? You're looking at the total change in distance from 2 to 6. So if you're driving, your distance, which is s, is always changing. We're looking for the total change from 2 to 6. That gives us our area. Anyhow, it'd be better to have an animation for this. Let f be a function that is continuous. All of our functions are continuous in here, right? We don't like functions that do this or have weird jumps, okay? On a closed interval, consider f to be positive. That means it's above the x-axis, all right? If f is the rate of change of a function, big F, so little f is the derivative of big F, they're using x here. Then the total change in big F, so Little f is the change in big F. The total change in big F as x goes from A to B is the area between the graph of f and the x-axis. So what they're trying to say here is, here's the change. This is the change in big F. So the total change in big F, total change in big F, which would be f of B minus f of A, the integral from A to B, is the integral from A to B dx. All right, that's what they need to be telling you. So this is the change in F, which we said was little f. This is also the change in F, in big F from A to B. All right, so they say it's the area underneath the curve. So if you have,
Yeah.
let's see here. No, I don't want to draw it yet. Okay, they don't give us a picture. All right, well, let's work an example. We'll lead up to that a little more slowly then. All right, so 13.3 shows the graph of 13.3. All right, making sure we're at 13.4. All right, we'll skip 13.3. So here's the graph of a function that gives the rate of change of the annual maintenance charges for a certain machine. Rate of change of maintenance charges. Okay, so the rate function is increasing because maintenance tends to cost more as the machine gets older. Estimate the total maintenance charges over the 10-year life of the machine. So instead of just maintenance charges, we have a rate of change of maintenance charges, which doesn't make this any easier to understand. All right, so we basically, the whole goal here is figure out the area underneath the curve. The way we find the area underneath the curve is we break it into little bitty rectangles. Okay, in this case, each rectangle is a year. So even throughout the year, the rate of change is changing every day, right? But we just say, okay, well, let's just look at this year. What was the rate of change for this year, right? So once a year, we'll check it out and we get this area of a rectangle. It's hard to figure out the area of an amorphous blob, but we know the area of a rectangle, right? If we did this every day, we would get a better average, right? If we did this every day, our rectangles would be really skinny, right? So the less often you do this, the more area, the more error you have, right? But the more often we do it, like if we did it every 6 months, our rectangles would be half as thick and you would have less error, right? So that's how we're going to set up our integral, which is the area underneath the curve. Basically, set up a formula that's just the sum of the areas of these rectangles. And the width here, we're going to call dx. So all we do is let dx get closer and closer to 0. We set up a limit. As dx gets closer to 0, you end up with an infinite number of rectangles that are infinitely skinny. And then you have no error whenever you add them up. They're called Riemann's sums. I don't think they care enough to teach all that. Try to read that one. The situation described preceding box with F being in the maintenance. So F is the maintenance cost. All right. And df dx is the, how do they say this? I hate their notation. Little f's and big f's. F is the maintenance cost, and little f is the rate of change function. So little, this is the maintenance. We have the rate of change of the maintenance, which they call little f, right here. Okay. The total maintenance charges change in F from 0 to 10. We would want to look at f of 0, the difference between time 0 and time 10, okay, is what we want to do. We can approximate this area by using the shaded rectangles. For instance, the rectangle marked with an arrow has base 1 and height 750. Similarly, each of the other rectangles has height 1. Anyhow, the width here of each rectangle is 1, and then to see the height, you just evaluate it. So like right here, this is 1. The height here would be f of 1. All right, or in this case, it's little f of 1, because this is the rate of change. Anyhow, the point here is you can get the area of the rectangles and add them up. That's all we really want to talk about there. All right, the preceding examples show that the area between a graph and the x-axis has useful interpretations. We develop a means of measuring such areas. So let's say we have this thing here, okay? Find the area under the graph. Well, this is a circle, a quarter of a circle, right? The area of a circle is pi r squared. So since this is a quarter of it, we just need to divide it by 4, okay? And we need to figure out an expression for, well, in this case, our radius is 2. So pi over 4, 2 squared, which is pi. That's the area of this guy. That's how I would find the area. Now we could use calculus to do it. Okay, they want us to use rectangles here. Okay, if we do it with just 2 rectangles, let's see here. There's different ways we could do it. We could do it left centered, like make the left side of the rectangle be touching. See, that would give us an overestimate, right? If we touched the rectangles on the left side. Or we could touch them on the right side, but then we wouldn't even have a rectangle right here. This would be a lower estimate, right? If we did the left side, and we did each side, we broke it down and made it just a half. So each one here is a half. That would give us a pretty good estimate, right? And you could do it either way, right? If we did it right justified, but we only did it by halves, that would be an underestimate, right? So how, what do they want us to do? Use rectangles to approximate area under the graph. All right, so there's lots of different approaches we could do. Let's see how accurate they want us to do this, though. I mean, the area is pi. We just figured out using the area formula. So they're going to do it left justified, which is the kind of standard way we do this. So if we do it like this with ones, the area of this guy is length times width. So it's 1, that's the length. What's the height? The height is this. Well, this is the number 0. We're just going to plug that into the function. Okay. And then the area of this guy is 1 times the height. Since this is the number 1 here, we just plug in the 1 into our function. And we just add those all up. Okay. And we could just break it down into as many rectangles as we want, depending on how accurate we want. And that's kind of okay, but really we want an exact answer. Okay. So we would set this up. We'd say, okay, y'all need to know the sum symbol. Y'all familiar with sigma? Right, the sum symbol. All right, so if you have like, say, 1/2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th. If you have a sum like this, let's say I wanted to go to infinity, right? I would say this is the symbol of 1 over 2 to the n, where n goes from 1 to infinity. That's really a 2 to 1 there. So you could write this like that, okay? That's what sigma is for. It's for sums. If I wanted this to stop at 2 to the 4th and not go to infinity, I would put a 4 here. So now n goes from 1 to 4, right? So you can make it like a finite sum, or you can let it go to infinity. That's how this symbol works. So what we would want is we want to add up the areas of all the rectangles, okay? So we'll start off with one rectangle to an infinite number of rectangles here. So we need the length times the width. Well, if we call each of these dx, right, that's the width, and the height is just f of x, okay? The limit, the area is going to be basically the limit as dx gets smaller, okay? It's going to be something like that. That's the rough idea. Here's they're just explaining each of the rectangles, you add them up, they get 3.49 or whatever. If we broke it up into smaller rectangles, you would just have more rectangles. And we're not going to go to the process of plugging all these numbers in because it's tedious. All right, so there's the area of this one, right? We plugged in a 0, and then we, now we're doing, yeah. The length is 1/4, and then the height is f of 0 here. The next one, the length is 1/4, and then we're plugging in a 1/4 to get this height right here. And you're just doing that with all of them, and you're getting a little bit better approximation than you did last time. Okay. All right, so what we do, we have n intervals. All right, so I'll do I equals 1 to I equals n. So we're summing from 1 to n here. The interval, you take the whole interval, in this case it would be 2, right? And you're dividing it into n intervals. So that's like your width. And then you need your height. So this would be like f of x sub I. So this would be x sub 1, x sub 2, x sub 3, right? And then the I is going to go from 1 over here to x sub n. Same kind of structure, right? We got a length times a width, or length times a height, and we're adding them all up. Area equals the limit as n goes to infinity, the sum of the areas of n rectangles. Don't worry, once we get through this, it's just going to be doing algorithmic. Here's how you do the integral. It's just trying to convince you the importance of it and what it means. And we're going to get pi. Or you could do it the quick way, right? Here's another picture. Just to convince you that the more rectangles there are, the less error there is. All right, so the rectangles, we'll call this length delta x, or change in x. All right, this is like a finite version. This is an infinitesimally small quantity. This is like, it could be a finite quantity, right? It doesn't have to be infinitesimally small. These are the same thing, but this is the calculus version because this is an infinitesimal. So basically, if you're going from A to B, right, you take that interval and you divide it into n pieces. So that's what your change in x is, right? Each one of these little thingies here has a width of change in x, right? Well, you're taking the whole A to B, that length, and you're dividing it into n rectangles. So that's what your change in x is. Okay, so that's the width of each rectangle. Then we label them. They have the x sub i's, the area of the ith rectangle. So this right here would be an x sub 1, this would be x sub 2, this would be your x sub 3. So generically, this would be an x sub I, where I goes from 1 to n, okay? So those are just the labels for the x's. So the height for each rectangle would be at f of x sub I. That's the height for each one. And this is the width for each one. So that's the area of the ith rectangle. This guy right here, right? And all we need to do is sum over the i's from 1 to n. All right. So our area, that's going to be this approximation where you have n rectangles. But we want to take the limit as n goes to infinity. So as this goes to infinity, that means instead of n rectangles, we're going to have an infinite number of rectangles. And if the width is this is the width, as n goes to infinity, the interval, this delta x, is going to get infinitely small. So we're summing over an infinite number of rectangles that are infinitely skinny. And this is the formula for it. But that turns into what we would call an integral. Okay. So you can see here the limit, we have the first triangle, the second triangle, the third triangle, up to the nth triangle. One last picture. So that limit turns into an integral. Y'all are familiar with this. All that we've done is put numbers here at the top and the bottom of the integral. Okay. So instead of getting a function, before we would be like, this is a big F, it's just some function. All right. This is going to give us an area. All right. So it's going to give us the area. All right. Let's see. The definite integral, you don't need to know any of this. Let's skip to the stuff you actually need to know to be able to do the problem. All right, last thing. This guy and this guy have totally different meanings. All right. This is a function. This is an area. It's going to be f of b minus f of a. Basically, you're going to get your integral, which is a function. If there's an a and a b, you're going to plug in b and a and subtract, and that's actually going to give you the area. Okay. This is a number, an actual area. This one is a function. All right. So we're not going to do this with the rectangles. I'm assuming you might have some problems in the homework, but the goal is to move beyond that. Approximate the integral from 1 to 4, 4x dx. Okay, here's how you do it. What is the integral of 4x? Well, we would add 1 to the exponent, divide by the exponent, right? That's what we've been doing. Now what you do is you put a straight line and you go from 1 to 4. So that means evaluated from 1 to 4. And then what you do is you plug in the first number, then you subtract, and then you plug in the bottom number. All right. So if these aren't here, you're done, right? If those are there, well, you need to evaluate your function from 1 to 4, which means plug in the 4, subtract, and then plug in the 1, and you're going to get a number. And that number is exactly the area underneath the curve from 1 to 4. Okay. Here they're going to break it into rectangles still, though. All right, so here's the first rectangle, x of 1. Here's your height. You plug in f of 1. Your second rectangle, oh, they're doing a halves. So it's 1.5. You plug it in, you're going to get the height, f of 1.5. The width here is 0.5, each one's 0.5. And you're going to get this underestimate. But we're not going to do that because it's tedious. That's all this stuff here is. We don't need 27 or 14 triangles this morning. Technology. Yes, you can plug these into your calculator. You should be able to. Scientific calculators should be able to do an integral, right? We've been doing integrals. Can you plug integrals into your calculator? I just go to Wolfram Alpha, or you can use Desmos. Okay. So yeah, here you'd want to make sure you have your parentheses, right, for the dx here, because the dx is applying to everything. TI 89. Yeah, I use Mathematica. Generally produce exact results. Other graphing calculators and spreadsheets provide highly accurate approximations. There are two ways to approximate a definite integral with a graphing calculator. I'm not going to go into that. Y'all can figure that out. Heat graphing calculator. $130 for nothing. I mean, you're not allowed to use graphing calculators on the exam, so you know why talk about it? Use your software. Use a calculator. No, we're not going to use a calculator. What is this? Here's a function. They want the area under the graph here. So if you want the area, you would have to integrate this. The integral here is x to the 4th over 4 minus 8x cubed over 3 plus 18x squared over 2 plus 5x. All right. And you need to evaluate that from 1 to 4.5. So plug in 4.5 everywhere there's an x. It's 18 over 2, 4.5 squared, 5. All right, so plug in 4.5, then subtract, and now plug in a 1 into everything. The 18 halves is what, 9? Make sure you put your parentheses here because we're subtracting this whole thing. And then it's just a whole bunch of arithmetic. And that's going to give you exactly the area under the curve between 1 and 4.5. Okay. So I guess this whole section is just, okay. Thought we were going to get into some calculus here, but it was all just rectangles. Y'all understand the rectangles, right? It's not a lot to understand. It's width times height. Add them up, right? Okay. Let's see. At a production level of X snowboards, the marginal cost in dollars per snowboard is given by this. So this is the derivative, right? This is the change in cost with respect to X. Okay. Find the amount added to the total cost when production goes from 350 to 400. All right, so they say the total change in C of X. This is C of 400 minus C of 350. That's what total change is, right? So that's the integral in C prime from 350 to 400, okay? So we just plug in C prime here, right? If you see C prime, right? C is the integral of C prime dx, right? You'll remember this from the last section. So C prime was like that. So we're doing the antiderivative of the derivative here, but we're looking specifically at a rate of change. So what we want here is, that was the last section. We're going from that to this. That's our step here. From an indefinite integral to a definite integral. We just have numbers here now. Okay. So if we were going to do this, if you're going to integrate this, we would square this dude out and then do it separately, right? This would be the integral 350 to 400. We would have an x. I could pull the 50. Come on now. We could pull this out of the integral. We would square this out. We would have x squared minus 1200x plus 3600. Is that right? 1000. I need 4 zeros here, there. And I need a dx at the end. Okay, so I have this 1 over 450. Then we integrate this. step by step, you're gonna get an x cubed over 3, 1200 x squared over 2, plus 36,000 x. We want to evaluate that from 350 to 400. All right. So to do that, first, replace x with 400. Okay. Subtract, and then replace x with 350. And you're going to get a number, and that's the answer. Are good? All right. This section, they just want you to plug this stuff into the calculator, because the calculators are typically doing the rectangle thing and doing an approximation. Okay. It's boring. Let's look at the calculus, 13.5. That section that we just covered should have been about the fundamental theorem. Oh, here it is. Fundamental theorem of calculus. All right. This is what I've been waiting for. All right, we now develop the connection between definite intervals and antiderivatives, which will explain the similar notion for these two concepts. More importantly, it provides a way to calculate definite intervals exactly. In the next section, we saw when f is the rate of change of the function big F and little f is continuous and non-negative, definite interval has this interpretation. Okay, so I just don't like the little f and big F stuff. It confuses me. I like to have one function. There's only one function going on. There's no need to give the more names, right? So they said little f was the change in big F, right? So what they should be writing here is integral from A to B of the change in big F is f of B minus f of A. All right, we don't need to have a little f and a big F, so this is the function, right? Typically, in a calculus, you would use little f because we like to use little f for the names of our functions, not big F, right? So if they're trying to dumb it down, they're just making it more complicated. That's it. This is the fundamental theorem of calculus. This is misleading. This is how it's always taught, and it's taught wrong. The opposite of the antiderivative is not, the opposite of the derivative is not the antiderivative. It has to do more with boundaries, right? They should have Stokes' theorem here, right? Because remember, like I said, if you have the area of a circle is pi r squared, the circumference is 2 pi r, which is the derivative of the area, right? The circumference is the boundary of the circle. It's all about the boundaries of things, okay? Here's a simple case, like if you think about it, here's a function, right? And if we're looking, say, between A and B here, right? There's this boundary and then the area. It's really more about that, all right? But here it's just kind of simplified in this special case, okay? But yeah, the integral is simply going to give you the area underneath the curve. That's all y'all need to know for in here. There's your fundamental theorem of calculus. The proof is discussed at the end of this section. Okay. Yeah, let's apply it. All right. This theorem applies to every continuous function. It's not going to apply to a function that has a hole in it, right? Like if you have like, here's A and here's B, and let's say there's a hole in it. Like, you do? Well, you would just look under, here and then under here and leave the hole out, okay? If the antiderivative is replaced by a constant for any constant, the conclusion is the same because C is eliminated in the final answer. Okay, yeah, because you're adding a constant and subtracting off the constant. All right, that has to do with the derivative of a constant is 0 anyways. I mean, if you add in a constant to the big F, it's going to change things because the area underneath this is not the same as the area underneath that. That's not what they're talking about. The variable used in the integrand does not matter. Okay, so the letter you're using in here, it doesn't matter. It's going to fall out. It disappears. Okay, so you can call this anything you want. Just like you could say, well, if f of x is x squared, I could say, okay, f of u is u squared, right? Or f of t is t squared. It's all the same function. It doesn't matter what you call your variable. It's the same thing going on here. Okay, it's not relevant what you name things. The last thing to emphasize here. In the definition of the integral, we call A and B the limits of integration. Typically, A is less than B, okay? If you want to switch these, you get a minus sign. All right, you can switch those, but you're just going to get a negative, all right? And if you're integrating from A to A, that means you're integrating underneath a point. The area underneath a point is 0. That's what they're saying here. They basically, a point has measure 0. You have a single dot, it's only a point. There is no area underneath it. You need an interval to have an area. And an interval has an uncountably infinite number of points, right? So even the smallest interval, if there's going to be any area underneath it, that interval has to be a piece of a line, has to be a line segment, which means it has an infinite number of points. Okay. It deserves its name since it's a key connection between differential calculus and integral calculus, which were originally developed separately without knowledge of the connection between them. So the areas underneath stuff and slopes, up until recently, we didn't realize there was a connection at all until we discovered, well, calculus. Okay. Well, actually, after we developed calculus, when we first discovered calculus, I don't think Newton knew the connection here. All right, so here's that notation, right? You just plug in the 2, subtract, and plug in the 1. So this guy, we need to integrate. So we pull the 4 out. This guy, we add 1 to the exponent, divide by the exponent, and we're evaluating this from 1 to 2. Of course, we want to simplify this first. This is t to the 4th, evaluated from 1 to 2. So we plug in the 2, we subtract, and then we plug in the 1. This is what 16 minus 1 is 15. That's how you do it. So this guy here, the integral of e to the stuff is e to the stuff divided by the derivative of the stuff, right? If I took the derivative of this, I would get that. And then we want to evaluate it from 0 to 5. So if you want, you could pull out the 1/2, all right? If you want to do that first. So we're plugging in the 5, we're subtracting, and we're plugging in the 0. All right, so notice I pulled out the 1/2. You can do that if you want. So we get 1/2 e to the 10th minus 1. right? Because this is just 1, e to the 0 is 1. That's the exact answer. You can plug that in your calculator if you want, but. Do this checkpoint here. We have time since we blew through that boring section. All right, this one. All right, we need to integrate this. We can pull the 5 out. The z becomes a z squared over 2. We're evaluating from 4 to 6. All right, I'm going to pull the 5 halves out. So I just have the z squared. So it's going to be 6 squared minus 4 squared. So 36 minus 16 is 20. So 5 times 10 is what, 50? Okay. This guy, e to the stuff, we need to do e to the stuff divided by the derivative of the stuff, evaluate it from 0 to 1. I'm going to pull that 1/3 out, and now we plug in the 1, subtract, plug in the 0. We got e cubed minus 1. We're good? Okay. This guy, this is z to the 1/2, so I add 1 to the exponent, divide by the exponent, evaluate from 1 to 9. I'll pull the 2/3 out. So now I just plug in the 9, subtract, and then I plug in the 1. Now we need to simplify. The square root of 9 is 3. 3 cubed is 27. We have 2/3 times the 26. Whatever. I want to do arithmetic. And I helped my neighbor with her college algebra. They use MyMathLab. It's so painful, like to enter in your answers. You know, it's like you can't type infinity or INF. You have to find your mouse and go click on that stupid infinity button. And it's like you have it has put those little blocks for like an interval. It's like no, you just gotta punch my computer. Yeah, do what you ought to do with that homework. It's so annoying. It's so annoying. I've never seen anything so tedious before. Okay. It's like a multi-billion-dollar company. You think they could come up with something better than that? I mean, that's why we're going to WebWorks, in the fall. It's free. It's it has its quirks, but we could actually change it ourselves. It's like a handful of people have created something that's just as good as what this billion-dollar company has produced. Yeah. Yeah. Yeah, it has the built-in help to yourself or whatever. Yeah, well, MyMathLab has the textbook and the automated homework, so it's 2 different packages, right? The web work is just the automated homework. It's not a textbook. You see what I mean? So you use it in conjunction with something else, and usually we use OpenStax because it's open source and free. So the thing about it though is we can do whatever we want with WebWorks and create our own problems. We can code it however we like, and the OpenStax is open source, so it actually gets better over time. There's this too much stuff. So I don't think they'll ever really improve this much. All right, so properties of definite integrals. They're the same properties of indefinite intervals. You could do all the things you thought you should be able to do. If it's a constant, you can pull it out front. If you have things added together, you can turn it into 2 intervals added together. You can take your interval. So if you have something like this, and you're going from A to B, right? You could break it up. Let's put a C there. You could do the integral from A to C, and then add to that the integral from C to B. So you could break it into pieces if you want to, which we're going to have to do because there's going to be issues. Like, what if you have something like this, and I want to know from A to B? I want to know the area. So we want to know these areas, right? Well, this, since it's below the x-axis, the integral is going to be negative. So let's say this is f of x, and let's say this is a point C, we would, if we want the area, we'd have to do the integral from A to C, right? But over here, since that's negative, we're gonna have to subtract, all right? Because this integral is gonna be negative because it's down here, so we need to put another negative to make it positive to get the actual area, okay? See what I mean? So if you have something symmetric, like this, if these are the same areas, if you integrated from here to here, you would get 0. And that's not what, they're necessarily wanting. So this isn't too hard, right? Once you know derivatives, you could do integrals. It's just the derivative backwards, right? And now it's just algorithmic, right? So this guy here, we would have 4x cubed over 3 minus 6x squared over 2 plus 7x. And we're evaluating from 1 to 7. Typically I would do this because we want to evaluate the whole thing, right? Not just the 7x. See what I mean? I don't know what notation the book uses, but oh, they put one next to each thing separately. Well, that's legit. But that's kind of, gee, just put parentheses. You don't have to put this thing next to each thing separately. That would be really tedious. Okay, not how you do it. And then you just plug a 7 in. So we have 4/3, 7 cubed minus, let's see, 6 over 2 is 3. Now we subtract. Make sure you put your parentheses because we're going to subtract the whole thing. Plug in a 1. 6 over 2 is 3. Yeah. So, because we're subtracting the whole thing, right? This is whatever. You see what I'm doing. Plug in the 7, subtract, plug in the 1. All right. The big mistakes y'all are going to do is not putting your parentheses here. Tedious little stuff, right? Okay. And this is it. This is like everything you're going to learn. There's a few more sections, but it's just this. This is your math. So, I mean, this class isn't really that hard, is it? If you really think about everything we've learned, there's like what? The power rule, the product rule, the quotient rule, the chain rule. And then you do them backwards. That's it, right? I mean, for 4 months of learning, right? Like, how good could you get at Call of Duty in 4 months? Right? And that's far more complicated than the 4 things we've learned this semester. It's just a matter of sitting down and doing your homework, right? And studying. It's not that hard. This is not quantum physics. There's only one variable here, x, right? I mean, here's a curve. Find the area underneath it. Right? The first half of the semester was what's the curve? What's the slope? 2 things, slope, area. 4 months of your life. Right? Let's do these here since we have 2 minutes left. There we go. So we integrate this. So this guy would give us a 4x squared over 2. This one gives us a 3x cubed over 3. We're evaluating from 1 to 3. So the 4 over 2 is 2. Replace the x with a 3. Now replace the x with the 3. Now subtract. Now plug in the 1. That's my little line here. Now we plug in the 1. So 4 over 2 is 2 times 1 squared is 1. And then over here we plug in the 1. 1 cubed is just 1. And then do your math. Same thing here. This guy becomes 6k cubed over 3. This becomes 2k squared over 2. And that becomes k. And we're evaluating from -2 to 3. So plug in a 3. The 6 over 3 is 2. Replace the k with a 3. 2 over 2 is 1. Replace the k with a 3. Replace the k with a 3. Now subtract. And everywhere replace the k with a -2. Again, 6 over 3 is 2. Replace the k with a -2. This guy, we have a minus, replace the k with a -2. And then this one, replace the k with a -2. And then add them all up and get a number, and that's the answer. That's the area underneath the curve between -2 and 3. Because this thing is, I don't know, we might be careful with this. We might have to look, graph this actually and make sure it doesn't cross the x-axis. Because again, well, no, here they just say evaluate the definite integral. That's the answer. It's different when they say find the area underneath the curve, right? Because if this guy looks like this, okay, the integral is exactly what we did. The integral would be that area minus this area plus that area. That's what the definite integral is. But if they said, hey, what's the area underneath the curve? We'd have to actually graph this and see where it crosses, because we'd want to subtract that off instead of add it, because that would be a negative area. You'll follow the subtlety there? Depends on what they are asking you. If they say indefinite integral, you just do the math. If they say find the area, you need to be careful, because if there is an area underneath the curve, the integral there is going to be negative, and you're going to want to have to put a minus sign to make it positive. All right. They'll emphasize that in the next couple of examples. But so far, this is it. Just do your little algorithm and get the answer. Questions? All right, let's get out of here. All right, it's so easy.